Today we are talking infrared spectroscopy. I'm going to show you how vibrating bonds in a molecule can tell us all about the functional groups present. This is a really powerful analytical tool. So, infrared spectroscopy is a type of vibrational spectroscopy. We're talking about the motion of atoms in individual chemical bonds. If we take a molecule such as hydrogen chloride, we can think of it as two atoms joined by a spring. In this model, the spring is the bond, and there is an equilibrium spring or bond length. If I compress my spring or I stretch my spring, that is going to require energy, and in both cases, there will be a restoring force that restores the spring to its equilibrium length. The more the spring is stretched or compressed, the more potential energy is stored in it. In terms of a bond, continually compressing and stretching a bond is, to all intents and purposes, a vibration. And if we return to our animation, we can see that the frequency of the vibration depends on two things: the mass of the atoms. So we know that heavier atoms cause the bond to vibrate more slowly, and the bond strength. Strong bonds vibrate more quickly. So, assuming our molecule is at a temperature above absolute zero, all molecules, all bonds have some energy. All bonds are vibrating. Now, we can cause them to vibrate more strongly if they absorb energy. You will remember the formula E equals hV, where E is the energy, H is Planck's constant, and V, I know it's technically pronounced nu, but I'm going to stick to V. V is our frequency. The frequency of the energy absorbed depends on the bond in question, but it's going to lie in the infrared region of the electromagnetic spectrum. So we're talking of frequencies from 10 to the 14 to 10 to the 13 hertz. And if we want to think in terms of wavelength, remember c, speed of light, equals wavelength times frequency. That equates to wavelengths in the 2.5 to 15 micrometer region. Let's take a look at the potential energy curve for a simple diatomic molecule. The first thing we'll notice is it's a very slightly different shape to that of the spring. So that was the potential energy curve for our spring model. And here we have the potential energy curve for our diatomic molecule for our simple bond, let's say, between hydrogen and chlorine. In both cases, we've still got our equilibrium bond length, and if I compress my HCl bond, it's going to require energy, and if I stretch my HCl bond, it's going to require energy. But with a chemical bond, obviously, if I continue to stretch it, eventually we're going to get to the point where we've pulled the atoms far enough apart and the bond will actually dissociate. This value here is our bond dissociation energy. Bond dissociation energy. There we go. So the bond is becoming weaker as we stretch it further and further. The other thing we'll notice is that our vibrational energy levels in molecules are quantized, and they're not evenly spaced. So if I want to move from vibrational energy level 0 to vibrational energy level 1, which means I'm making my bond vibrate more strongly, we can see that with the waves on the diagram, it's going to require a specific frequency of infrared radiation to be absorbed. And the frequency of energy needed to make, say, an OH bond vibrate is going to be different to the frequency of energy required to make a carbon-oxygen bond vibrate more strongly. And this is what we're seeing on an infrared spectrum. This is the infrared spectrum for ethanol. So if we remember, ethanol looks like so. We've got 2 carbons. We've got a number of carbon-hydrogen bonds, carbon to oxygen bond, and an oxygen to hydrogen bond. Now, if I take a sample of ethanol and I shine all the frequencies of infrared light onto it, each bond will absorb its own specific frequency of radiation, and that frequency of radiation is going to disappear. So transmittance, here we've got 1, often it's as a percentage, for example 100%, so that's all the infrared light coming out the other side of my sample. But we can see that certain frequencies are being strongly absorbed by my ethanol molecule. These are the frequencies needed to increase the vibrational energy of certain bonds. And we can match I know they're troughs, but we call them peaks, the peaks in the spectrum to specific bonds. So we know that that first peak there corresponds to an OH bond stretching. So if I want to make my OH bond stretch more strongly, vibrate more strongly, it's going to be absorbing this particular frequency of infrared energy. This peak here is for carbon-hydrogen bonds, and this one down here for carbon-oxygen bonds, and where you can use a data sheet to find out this information. Now, one of the things we'll notice is the x-axis is not in frequency, not as we know it, it's not in hertz, it's in wave numbers, centimeters to the -1. Often, this x-axis is also non-linear, so be really careful when you are reading a value off it. So what are wave numbers? Well, they were invented to try and make the scale a bit easier to use, because obviously with frequencies, we're talking, say, 10 to the 13 hertz. Those are very big numbers. Where does wave number come from? Well, let's go back to speed of light equals wavelength times frequency. If we know that to be true, then we could also say that 1 over wavelength is a direct measure of frequency. And we end up with these numbers, say 1,000 to 4,000, rather than working in 10 to the 13 lots of hertz. So let's have a look at this. Okay, so 1 over wavelength, which is our wave number. So let's say that is 1,000 to 4,000, which is roughly the interesting part of the wave number scale for an infrared spectrum. That corresponds to wavelength of the region. We've already seen this, roughly 2.5 to 10, 12 micrometers. So sorry, wave number is centimeters to the -1. Wavelength is micrometer. And in terms of frequency, we've got around about 10 to the 14 hertz, and that would be around about 10 to the 13. So that's how wave number relates to both wavelength and frequency. Now, there must be a change in the dipole moment of the molecule during the vibration for the vibration to show up on the spectrum. Our dipole moment is equal to the charge times the distance. So if I take a molecule such as HCl, we know that the hydrogen is delta positive, the chlorine is delta negative. So when I compress or stretch this bond, the dipole moment is going to change. However, there are some molecules, homonuclear diatomics, so we are talking about molecules, diatomic molecules, where both atoms in the molecule are the same. Because they have the same electronegativity, there's no charge difference between the two atoms, we're not going to see any change in dipole moment, and so we're not going to see a peak on the spectrum for these types of bonds. Our simple diatomic molecule, such as HCl, only has one vibrational mode open to it. It's able to stretch. But as our molecules become more complex, they're able to vibrate in many different ways. So if we think about water, of course, is a bent shape, and we can see that we have symmetrical stretching, asymmetrical, and it is also able to bend. These are three different types of vibration. So on an infrared spectrum for water, we'd expect to see three different peaks, and we do, sort of. So this is the peak for the bending, for that vibration, and that happens at around 1595 centimeters to the -1. And then we have asymmetric and symmetric stretches. So the symmetric is at 3652, and that one is 3756 if we're going to be completely accurate. So we've got three different peaks, but we can see that these two are very close to each other, and in reality we kind of get a broad band rather than sharp peaks. Reason for this, in water in particular, we have hydrogen bonding between our molecules, and that affects the ability of the bonds to vibrate. We can see the same thing with carbon dioxide. There's my CO2 molecule. Again, it has the ability to show symmetrical stretching, asymmetrical stretching, and also bending. And in the case of carbon dioxide, we can use infrared spectroscopy to measure the CO2 concentration in the atmosphere. And this is what I'm going to pronounce this wrong, Mauna Loa Observatory in Hawaii has been doing for about 50 years. It's at an altitude of around about 4,000 meters. Isn't that a fantastic photo? So there's very little interference with carbon dioxide concentrations fluctuating from day to day because of human activity or vegetation. Around about, there is none. Air samples are collected every hour, and the carbon dioxide concentration is monitored. And we can see from the infrared spectrum for carbon dioxide, that equates to the bending of carbon dioxide, and this particular peak for the asymmetric stretch. Now, there's no symmetrical stretch for CO2. Why would that be? Because there's no change in dipole. If we think about carbon dioxide, because it's a linear molecule rather than bent like water. A symmetrical stretch won't lead us to a change in dipole moment. So we just see a peak for bending and for the asymmetric. If you scroll through the blurb below the video, you'll see that there's a link. You can download a PDF of all the diagrams and the spectra I've used in this particular video, which you can annotate and add to your notes. I should probably have mentioned this at the beginning of the video, but hey, better late than never. If you've got any questions, then please leave them in the comments below and I'll get back to you as soon as I can. Hit the like button and subscribe. It makes a huge difference to a small channel like us. See you next time.